Hey there. So I'm going to be having you guys do today's lessons through the video here. And so your teacher should be now handing out to you our new packet. We just finished up with our scientific method one. So we are going to start a new packet. I need you to do 3 things on this packet. Put your name up in the top. Remember, there's not necessarily a spot, so just find a place to put your name and the hour. So 5th hour, 6th hour. Then the third thing that I want you to do is open this up and crease it like we did the last time. So we took like 2 pages at a time and kind of folded them over the staple. Run your hand along the edge there and crease it. Okay, so 3 things. Get your name on there. What hour are you in? And then go ahead and crease it. So I'm going to have you pause the video here until everybody is ready to go. Okay. So the front of your packet looks pretty much similar to our last one. We have 3 concepts now instead of 4. Each one is a little bit longer though. And so our essential question is, how do forces cause changes in an object's speed and direction of motion? That's our essential question up at the top. So forces, you probably have an understanding of maybe what that is, right? Some type of thing that causes a change. In an object's speed, most of you can probably describe what speed is. And direction of motion. So this word direction, we're going to be using terms like north, south, east, west, maybe even left, right, up, down. Those are going to be ways that we can describe the direction of the motion. All right. So just looking over this real quick, we have the 3 concepts. Concept 1 is obviously what we'll get into first. We're going to describe what motion is. And so we have words like distance, speed, velocity. Concept 3, we'll talk mostly about acceleration. All right, and you can see that's our only vocab word there. Concept 3 really gets into Newton's laws. Remember that laws are not subject to change. They have been proven time and time again. So Newton's laws apply to many parts of physics. So that's where we're going to get into some of these words here like inertia, force, and talk about weight. So look at the practice questions under concept 1. All right, questions 1 through 7. And they should remind you of a different subject that you all love in school, right? A lot of these look like math problems, like word math problems, right? So they are essentially. Math and science do go really hand in hand together, especially in 9th grade and then also in 11th grade. You'll get a lot of math and science in both those years. So it is what it is. We'll learn it. It's not necessarily anything too hard. Most of it's stuff that you kind of understand the process already. Alrighty. So I'm going to have us go ahead and open up to page 2 of your packet. So page 2 looks like this. Oops. All right, so remember how this packet's laid out. We have our main words here. You'll see them pop up and you can go ahead and write the definitions behind them. These are also like vocabulary words. So if you want to highlight them, you sure can. We also will be using this area here. I always call that the margin. So make sure that you put stuff over there when I tell you to. All right, so let's get going on concept 1 here. So what is motion? If I were to ask you to describe it, most of you would say something about moving. And that's pretty much true, but this is the technical way to describe it. So when an object changes its position, it can do that and change direction. It can do that by moving forward, backwards, speeding up, slowing down. Lots of ways you can change position. You do not have to write this. Okay. So you do not have to write this. It's in italics. It's optional. If you do want to write it, you can. So how do you know if something is moving? Well, most of you would just be able to see, well, I would be able to see it move, right? So if you look at this picture of this car, how do you know it's the car that's moving? Well, it's blurry, yes. That gives you a clue. Also, you look at things that are not moving, that you know aren't moving, right? Like the tree. I know the tree doesn't move. And so if the car is moving past it and the car is, going by it, and I know that the car must be moving, not the tree. And so whether you think about it or not, you are constantly looking at reference points to decide what the motion of something is. So a reference point is an indicator that positions you. All right. An indicator that positions you. It lets you know what is, like, you use reference points in terms of trying to figure out what is moving and what is not moving. Most of the time, reference points are immovable objects, like this tree or the trees behind there. So reference points are often immovable objects. They don't always have to be. I'll give you an example here in a bit of what you could still use a reference point and it's not necessarily immovable. So if you were on a bus in a big city and you look out your window, right, and you're trying to decide, okay, is the bus moving, or is the rest of the traffic moving, like the cars outside your window? Are they moving, or are you moving? Right? Because it'll depend on, where you're sitting. If you're, in the car versus the bus, let's say you're in the bus. So how do you know, or what can you look at to figure out, if it's the cars that are moving or you? Well, we look at a reference point, something that you know is not moving, like a building. You can also use like a train. So most of you have probably, seen trains on 14 as you've either driven to New Ulm or driven back and driven kind of right beside them. Well, you probably know that the train is moving by looking at it, right? And comparing it to other, things out there. But you can also tell the speed as, which one's moving faster, you or the train. Again, you're using reference points, to figure that out. So again, don't think too much into it. Again, reference points are really just objects that we use to indicate, where, if something is moving or not. All right. So now that we know how to figure out if something is moving, now we need to figure out how to measure it. So how do I measure movement and motion? The easiest way to do it is with distance. So distance is, we're going to use a variable, which are letters. Okay, in this case, a lowercase d. Make sure it's lowercase. So whenever you see lowercase d, that will stand for distance. How far an object has moved. Makes sense? This is optional. If you want to write this in, you can. These are the units that are possible for us to measure distance in. These are some of the common ones that you'll see in here. Meters, inches, feet, miles, MI, that's what miles stands for. Even like centimeters, millimeters, I mean, those are all distances, not very big, but they're distances. Okay. So distance is just how far an object has moved. So it's going to be some type of length measurement that you're going to be using. You'll notice that I do have a mixture of metric and non-metric units in here. Meters and centimeters would be metric. But inches, feet, and miles, those are just sort of English or American units. I do use both in here. So you'll kind of see both. I don't stick necessarily with one over the other. you will see both. All right. Now, another way that we can measure motion is how far are you from where you started? Okay. So how far are you from where you started? That is going to be the definition for displacement. So this is our next word. So the abbreviation or variable that I use for displacement is a little different. It actually includes two things. It has this triangle here. That's a little triangle. I'll talk about that here in a second. And then a lowercase x. So make sure you write this down after so you get used to seeing this and using it. So your displacement is how far and in what direction are you from your starting spot? What was your change in position from start to end? So the difference between your starting point and your ending point. All right. So on your page here, in the margin area, right next to the word displacement, I want you to write the delta symbol there, the triangle symbol. This, I kind of read this as delta. I don't read this as triangle. I can also read this as like change in. All right. So you may have seen this in math before if you are in maybe one of the more advanced math classes. These symbols here, if not, you'll see it a lot more, and you'll see it a few times here in science. Delta means change. It always means that I'm going to be measuring sort of like a before and after. So what's the difference? What was the change? One that we often use this for, and we haven't gotten to it yet because it's more of our matter unit, which is more of the chemistry part that will start in like January, would be like, what's your change in volume? What's your delta volume? Like, what's your final volume minus your initial volume? So you'll see this more and more, but our delta usually involves some sort of like two numbers that are getting minus from each other. So it's your difference, it's your change. Okay, how much did it change? All right, let's go back to this here. So here's a couple of things that I want us to think about. All right, if this is my starting spot, so I'm going to put an X here and then put an S. And if you want to draw this off to the side in your margin below the delta that you drew, you can. If you just kind of want to watch, you can too. So if this is my starting spot, X, and I go this way over here and I end over here and I have another X here. Sometimes I'll just put the E's and the S's. Sometimes I won't put the X's, but I usually like to indicate what my starting spot is and what my ending spot is, especially if I'm dealing with displacement. Okay? So in this case, how far, what is my distance traveled? Let's say this was 20 feet. Okay? So my distance, my lowercase d, is how far did you move? 20 feet. That would be my answer. Displacement is a tiny bit different. It's how far are you from the starting point now and what direction. So it's your distance and direction. So when you give me an answer for displacement, you need to have two things. What's the distance and what is the direction? Now, directions, okay? There's a lot of you in here that may not know these off the top of your head. So somewhere on the top of your paper, top corner is fine, wherever. I want you to draw a compass. So you can start by drawing a plus sign, okay? And your paper is always, the top of your paper is always going to be north, all right? So you'll put the N at the top of the plus sign. So the top of your paper is always going to be north. Towards the right of your paper will always be east. So you're not really going to use like the directions in the room because everybody's orientated in my room a different way. So it would not be the same for all of us. Our papers are all, the same though. So never eat. And then S is south. Now, most of you probably heard the mnemonic, never eat soggy waffles, to remember the order. So don't forget that, okay? I'm not always going to give you that. And sometimes if I do, I just give you it like this, and all I do is label the N. So you have to make sure you know the rest of them. So in this case, I want to know, what is my direction? Well, see how I drew this arrow from my starting spot to my ending spot? If you draw an arrow with an arrowhead, from your start to your ending spot, that arrow tells you your direction. Okay? So I would say, as far as displacement goes, for this example, my displacement is 20 feet, and then I need to add my direction, 20 feet east. That is how far I am from where I started to where I ended. And it's my direction as well. I'm 20 feet east of my starting spot. Okay? Because 20 feet, you could be 20 feet north, 20 feet south, 20 feet west, and each one would be in a different spot. So that's why when we use displacement, it helps to kind of orientate us. All right? This one example here, I am going to have you write down in the margin of your paper. Again, it can kind of go sort of right here on kind of next to the example where it says example here. So go ahead and write this example or this one that pops up here. I want you to write this down because this question comes up on tests and quizzes more than once. It's kind of a tricky one. So write this down. You can put EX and then write this down. So again, you're writing this in the margin of your paper next to the word displacement or next to example number 1. So it says a runner runs around a 400-meter track. All right, so basically it's once around the track. Like our track outside is 400 meters. Most tracks are. Okay, so the runner runs around a 400-meter track, and they end up where they started. So what's my distance? How far did I travel? How far did the runner travel? And what is their displacement? How far are they from their starting point and in what direction? Okay. So distance, how far did they run? Well, let's draw a picture of this because pictures work wonders. Move that out of the way here. So let's say I'm starting here. I'll put my XS right there. And I'm running around the track. Okay. And I start right where I end. So my XE is also right there. How far did I travel though? The track itself is 400 meters all the way around. So I ran a distance, or the runner ran a distance of 400 meters. So write this down. again, in the margin area next to your drawing, your total distance traveled is 400 meters. You actually, ran 400 meters. Now, what's your displacement though? Distance and direction of an object's change in position. What's the difference from their starting point to their ending point? My starting point was right here. So is my ending point. So if you go around in a circle, have you actually displaced yourself? Are you actually away from your starting spot? Any distance or any direction? The answer is no. So my last little bit here, my displacement is 0 meters. And I don't even need east, west, south, north because I didn't technically get displaced north, south, east, or west of my starting spot. I ended up exactly on my starting spot. So again, my displacement, if I'm going in a circle and I end where I started, will always be 0. And it doesn't actually even have to be in a circle. If you go in a, around the block to your house and you end right where you started, again, your displacement is 0. All right? So keep that in mind. All right, let's take a look at example number 1. It says if a soccer player runs after his opponent 50 meters north, then turns around and chases him 20 meters south, what's his distance and displacement? Okay. So the picture here is already kind of drawn for us on the board. If you want to draw like a simple one of this on your paper, you can. I don't need you to necessarily draw like the soccer field and all that stuff, but just draw something like this. So XS, that's where I'm going to start from. So I went 50 meters north, and then I turned around and came 20 meters south. Now, technically, let's assume that they sort of run on the same line or the same pathway, so they didn't really travel much like this way. However, it doesn't technically, say that, but I can assume that unless it tells me I actually ran a certain distance left or right. Now, you'll notice that, the drawing on the board is a little bit more exaggerated there just so we can see it, but really you're coming back pretty much on the same line, okay? So I'm going to label this. So this was 50 meters north, and this was 20 meters south, it said I came back. And this is where I am ending, XE. Okay. So to figure out your distance traveled, this is just how long did it take you, or how far did you actually run? That's all we want to know. Okay. So my distance is unknown. You don't necessarily have to write the D with the question mark and the delta X with the question mark. I will have you write this though. So the distance traveled is your 50 plus your 20. And when you go ahead and you add that up, you get 70, and then make sure you bring your units along with that, meters. Okay? So the total distance that you ran was 70 meters. Makes sense? Now, your displacement, again, is how far are you from your starting point now? Okay? So let's look at this one here that I drew myself. And I really only want to know what is my distance from this starting spot to this ending spot. What is my distance and direction? So my distance is the difference between the 50 and the 20. So you have to, you ran 50 minus the 20, okay? So your delta X is 50 minus the 20. So 50 minus 20 is 30 meters, right? So that is the distance from this black line or black arrow here. From my starting spot to my ending spot, I displaced myself 30 meters. I'm 30 meters from my starting spot, not 70. I'm only 30 meters from my starting spot. The last thing that I need is a direction. So am I south of my starting spot? Am I north of my starting spot? That's why I have you draw an arrow from your start to your ending. Okay? If you draw an arrow from your S to your E, that tells you your direction. This direction here, this black arrow is pointing north, according to my paper. So my total displacement is 30 meters north. All right. So what I want us to do now is we're going to work on some practice problems with these. So go to page 6. Go to page 6 in your packet. Okay. So it says, answer the following questions, sketch a picture before solving, and make sure to show all your work. You may need a separate sheet of paper. I think you can probably fit it on here. You just maybe have to write small. The main thing is I do need to see a sketch for each one of these. We are only going to do 1 through 4. Yeah, we're just going to do 1 through 4. Okay. So number 1 says PJ likes to ride his bike around the block. If he rides out of his house west, the sidewalk circles his block and brings him back to his doorstep 0.35 miles later. Find his distance and displacement. Okay, so when I draw this, it should be a little bit more clear. PJ likes to ride his bike around the block. If he rides out of his house west, then the sidewalk circles the block and brings him back. Okay, so here is my starting spot, XS. West. Okay, west is this way, so I'm going to make my drawing go this way. Then it says he goes and circles the block. Now, it doesn't mean like a circle, but it does mean that he just goes around the block like this. Okay. And so his ending spot is back to his doorstep. So his XS and his XE are at the same spot. That should tell you something. Okay. The total distance around the block was 0.35 miles. 0.35 miles. So distance and displacement. For each one of these, I need a D and I need a delta X. Okay. So you always want to have those ready to go. So your distance, pretty easy. It's actually just given to you right in the problem. 0.35 miles. Again, how far did he actually walk or bike? His displacement, though, this is similar to the track example. All right, he did travel, but he didn't actually displace himself. He's still in the same starting spot or he's in the same spot as where he started. So your displacement is, you can either write 0 or 0 meters if you want. All right, again, so if you end up in the same spot, okay, then you have not displaced yourself. Number 2 says Nicole parks her car at Target and walks 150 feet north to get to the store. On her way back to her car, she walks 50 feet before pausing when she sees a sign for a discounted iced coffee. Find her distance and displacement. So at the point that she stops, I want to know her distance and displacement. So this is going to be very similar to the soccer example. Okay. So I know that it tells me that she goes north and then back to her car. So that would just mean straight back. So I need to kind of draw mine going up and down like I did. So XS is where I'm starting. That's her car. So she goes to Target here, right? And then she comes back and she walks 50 feet. Now, with your drawings, you want to try to make them somewhat accurate. Okay? This was 150 feet. This was 50 feet. Make sure you label these. Maybe zoom in a little bit here. Okay. So 50 feet and 150. You see how, like, I can probably tell that 50 feet is like a third of 150. Make sure that your drawings are somewhat similar. So don't, exaggerate them too much, or, try to make them as close, to real as possible. And then that's where her ending spot is. So XE. So I need to measure from my her total distance traveled. So that's just D, right? So she went 150 feet north. Let's just say she went to the front of Target and turned around. She didn't actually go into Target and walk around. So she traveled 150 feet plus the 50 feet, which gives her a total distance of 200 feet. Okay, so she traveled a distance of 200 feet. Now her displacement, delta x. Okay, again, that is the distance from her starting spot to her ending spot. So again, I implore you to make an arrow from your x, from your xs to your xe, s to e, start to end. Okay, and you should see that this goes north. I know it kind of goes at an angle. That's because my drawing, I need to make it that way. And what is this distance here? So how far is that? Well, it would be 150 minus 50. Okay, so she is 100 feet from where she started. This is 100 feet. So she's 100 feet from where she started. And is she north of where she started, south, east, west? When you draw that arrow, you clearly see that she's north of where she started. Okay. Let's take a look at 3. So 3 says Maria's trying to meet her friends at the pool, but construction is blocking her path from the parking lot directly to the pool. Because of this, she has to walk 20 feet north, 35 feet east, then 20 feet south to get to the pool. Find her distance and displacement. So I have to do a drawing for this, right? So I'm just going to have my drawing start somewhere down here. So I have XS, that's where I'm starting from. It says she walks 20 feet north. Okay, so I'm going to draw an arrow, go up there, and then she walks 35 feet east. So is that to the left, to the right? Should be to the right. Okay, now you want to make that arrow a little bit longer because this was 20 and this is 35. Okay, then it says she walks 20 feet south to get to the pool, which is where she's ending. So that was 20 feet south. So my job is still the same. What is my total distance travel? I went 20 feet, or she went 20 feet plus 35 plus 20. So 20 plus 35 is 55, plus 20 is 75. And then make sure you use your right units, feet. 75 feet is her total distance traveled. Now, this is where my displacement is different now, okay? So my displacement, again, is the distance and direction from my starting to my ending spot. So as I told you, draw an arrow from your S to your E. Draw an arrow from your S to your E, directly from your S to your E. Now, how far is that arrow? In what direction? That's what you need to answer. Okay, so to figure out my delta X, I want to know how far is that arrow in what direction. So let's do my distance first. Well, it's the same distance as up here because she just walked basically in a block or a rectangle, right? So this distance is the same as what she walked up there. So it's 35, and then feet. And the last thing that I need to do is my direction. So what direction is that arrow pointing? East. So her displacement, how far is she from her starting spot, is only 35 feet east. Basically, if there wasn't construction, she would have been able to walk the 35 feet east to get to the pool. She would have been able to go from S to E, but since there was construction, she had to go up, around, and down. So she had to travel a longer distance, but her displacement is only 35. All right, so we got 2 problems left for today. Number 4 says, Mally loves to make herself dizzy. She spins around in place 7 times before falling down right where she was standing. Find her distance and displacement. Okay, so this one's a little bit of a tricky one too. Let's have an XS for my starting spot. She spins around in place. So, really she's just going like this, okay, 7 times. I know it's kind of hard to draw on here. If you wanted to do like XS and then just kind of do a circle around there like this, you can. And she ends in the same spot. So assuming that her feet only turned around in a circle and didn't actually move like, 2 feet this way, 1 feet this way, her total distance that she actually moved was 0. All right, so 0 doesn't even give me a unit, but we'll just say 0 meters. All right. So again, because she did not she moved in a circle, but she didn't actually move off of that starting spot at all. All right. Not to even come back to it. Her total distance actually traveled is 0. Okay. She spun around in a circle, but that's not traveling. In order for you to have distance, you have to, have a move away from a starting point. Okay. Now, displacement, which is delta X, is a little bit easier now this time that we have this idea down. So delta X, my displacement, how far are you from your starting spot? Also 0 meters. I don't even need I don't obviously need a direction if I have no displacement. So don't worry about putting directions when your displacement is 0. All right. Actually, that was the last one that we were going to do because the next ones involve using something that I have not gone over with you yet. All right. So I will end the video there for today. And I will plan on seeing you guys tomorrow.